Alright, so welcome to the video for the shell method, the third method of finding a volume of a solid formed by rotating a two-dimensional area around an axis of rotation. And so you've done discs and washers, and now we're going to do shells, which you can see by the pictures I've shown here, are finding volumes of hollow cylinders. And in fact, the cylinders are going to be so hollow, they're going to be so infinitesimally thin that they're basically going to look like just circles with heights on them. And so if we add all those up, you can see that we approximate the volume of a sphere with cylinders as well as many other shapes. And here's how it works. Imagine I wanted to take this red region and rotate it around the y-axis here. And I'm going to draw kind of the go shape on the other side. You can imagine what this would look like rotating around 360 degrees. And I have a vertical rectangle instead of a horizontal rectangle just because might be easier to do it this way. You can see that this is a quadratic function that I would have to somehow solve for x, and that would be difficult to do. And so I'm going to just theoretically look at this picture and imagine I did find a way to find this hollow shell here. If I cut it down the middle like that and unroll it, so imagine taking this whole thing, cutting it right there, and unrolling it into this rectangular prism, I should say. Well, the width of this really thin rectangle would be delta x in this example. So there it is there. The distance around, the rolled out distance would be the circumference of that circle, which depends on the radius. And what's the radius then? Well, it's on the x-axis, so this r value is going to be basically whatever x value you're at. And then the height is going to be the difference between the top of this function, f of x, and the lower function, g of x. So height is going to be f of x minus g of x. The radius, the distance from the axis of rotation, will just be whatever that x is. And then I have to multiply by the 2 pi x. So essentially, I will be integrating, it looks like from here, I don't know what the bounds of integration are going to be here. It's a to b of 2 pi times the radius, x, times the height, which is f of x minus g of x, all with respect to the variable x. And of course, if I was doing this 90 degrees clockwise, you can see that my rectangles would be horizontal, and therefore I'd have a delta y, and this would be the difference of maybe f of y minus g of y, and the radius would just be the y values. And we've kind of now found the general basis of the shell method. So I will do an example here just to give you a theoretical basis of what we're doing. So I have this function, y equals x minus x to the third power, and I've encased it between the function, the x-axis, and so you can see that I have this blue region that I'm trying to rotate, not around the x-axis, which would be really easy if I was using the disk method, but rather I'm going to be rotating around the y-axis, right over here. And I made kind of my ghost shape here. It's not perfect, but I want you to get the idea of what this would look like. And so what I need to determine on this picture is what this height would be. So the height, then, would be the difference in the upper boundary here and the lower boundary there. So it's going to be the first function of x, f of x, which is equal to x minus x cubed, and the g of x, the lower end of it, would just be y equals 0. So if I subtract that, f of x minus g of x, which is going to be the height of that rectangle, it's just going to be f of x minus x cubed, because the axis of rotation is the line y equals 0, or g of x equals 0. All right, so we have that settled. That's the height. Now the width of this hollow cylinder is going to be delta x. It's going to be with respect to x there. I want that to go all the way as close to 0 as I can. And finally, the radius. How far away am I from the axis of rotation? Well, since the axis of rotation is the y-axis, I would just basically have to take x and subtract the distance from the rectangle to the axis of symmetry. So in this case, it's just going to be x minus 0, because the axis of rotation is x equals 0. So my r would be x, my h would be this, and therefore I can just set up the integration from 0 to 1. That's where my radius stops. That's where my function intersects here in my bounded region. That's going to be 2 pi times the radius, x, times the height, x minus x cubed, all with respect to x. I can pull out the constant here. 2 pi goes on the outside. integration from 0 to 1 of x squared minus x to the fourth dx. And you can see after doing integration using the fundamental theorem of calculus as well as the general power rule of integration, I get 4 pi over 15 units cubed. And you get the decimal approximation of that. And just so you get an idea of what this would look like, well, from above, it's going to be kind of like a flat inner tube on the bottom. There's going to be kind of this hill on both sides. It's going to rotate around like this. It's going to kind of have this divot in the middle, if you will. And so why would the disk and washer method be difficult? Well, if you had perpendicular rectangles like this, you somehow have to find the height of that rectangle. And that function is x minus x cubed. You have to somehow solve that for x alone. And that'd be pretty difficult, if not impossible, using algebraic techniques. So in summary, this is what the shell method is all about. If you have horizontal rectangles, and you want to rotate it around a horizontal axis rotation, you're going to use the shell method in terms of functions of y. 2 pi from c to d of py, hy, dy. Whereas if I have vertical rectangles and a vertical axis of rotation, I'm going to use 2 pi from a to b of px, hx, dx. That was a lot of alphabet soup, but here's another practical demonstration. Let's say that I have x equals e to the negative y squared and the y-axis. So that means that between 0 and 1. And so I have this blue region that I want to rotate around the x-axis. And so I'm going to kind of mirror it here so you get an idea of what that might look like. It's going to be three-dimensional here. So in summary, it's going to have sort of this bell curve top like this, and looks like a rectangular base. So it looks something like that maybe, but rotated 90 degrees on its side like this, as you can see. I don't know. Something like that. I'm not being a very good artist today. But let's go ahead and use our shell method to integrate this. So first you have to identify the radius. How far am I away from the axis of rotation? Well, the axis of rotation is x. And as I integrate, again, since it's in terms of y, I'm going to start from the bottom and go to the top, just like Drake, right? That's another terrible math joke. So I'm going to integrate from the bottom to the top. And so my integration bounds are going to be from 0 to, it looks like, positive 1. That's where the 0 to 1 is my y. 2 pi, and what is the radius? It's just going to be the y value, however far I am from that axis of rotation, right? Now the height, h of y, is going to be the difference between my black line and the y-axis. So in this case, it's going to be e to the negative y squared minus the axis of rotation, and of course with respect to y. I can pull the 2 pi out in the front. From 0 to 1, it's going to be y times e to the negative y squared dy, like that. Now, again, since we haven't done integration for a while, it's going to go through the u substitution on this one. U is going to be negative y squared. That's going to make du equal to negative 2y dy, which again, if I'm using a substitution method of integration, I'm going to take du divided by negative 2y, and I'm just going to plug in what I know. Don't forget, however, to change the bounds of integration when I do my u substitution. So since I was using y values here, I need to take negative y squared, which would give me 0 and negative 1 on the top. That's by plugging that into this equation. To get my u values of integration, I take negative y squared. And notice the negatives on the outside, not on the inside. So now I have y and e to the u, and then dy was du over negative 2y. So again, these y's are going to divide out. That negative 2 and positive 2 are going to divide, so I'm going to get negative pi from 0 to negative 1 of e to the u du. Of course, I don't want to have the 0 on the bottom that's an improper integral, so I'm going to put another negative up front to make positive pi, and switch the bounds of integration from negative 1 to 0 of e to the u du. And of course, well, it went all the way down. Not sure why it jumped so far. So I have pi times, it's going to be the integral of e to the u is, thank goodness, e to the u, evaluated from negative 1 to 0. So it's going to be pi times 1, e to the 0 is 1, minus, oops, that was weird, pen is, ghost pen, minus 1 over e, it's e to the negative 1. So therefore you have pi minus pi over e, units to the third power. There you have it. You can get a decimal approximation if you'd like to get some sort of semblance of how much volume you've accumulated. But that's how you do the shell method. And again, if I wanted to use the washer method, I could do that, but I'd have to separate it indefinitely to two integrals. I could basically integrate this much, right, with just a rectangle, right, or a cylinder that would rotate around, but then I'd have to solve this for y, which would take the natural log of both sides. I would multiply by -1, then have to take the square root. And that's going to be a really nasty kind of thing to solve for. Summarize, we have two methods, the disk and washer method and the cylindrical shell method. So if I'm doing the disk or washer method, my rectangles are going to be perpendicular to the axis of rotation. So you can imagine that I'm going to rotate this around this way and get sort of a hollow funnel cake here. And so that's going to require me, my radius here is going to be r of y minus the lowercase r of y, where this is the outer function, capital R of y on the outside, and the inner function would be the lowercase r of y. And that would be the radius, basically, the outer radius minus inner radius. And so then the height, that's the height of the rectangle, or the washer, excuse me. This is going to be delta y. The difference in y will be the width of those rectangles. And so I'm using the area function, so it would be from c to d of pi times big R of x minus little r of x, so squared, minus little r of x, y, r of y, excuse me, I apologize. Second time I've tried to record this and I made the same mistake both times. So there you go. Capital R of y squared minus lowercase r of y squared dy. And of course, if I have a vertical axis of revolution, then it's going to be the same thing, except I'm using different bounds of integration, which are x values. I'm going to have capital R, pi times the capital R of x squared, which is going to be the outer radius, minus the, again, I should say that pi is multiplied by the whole thing here, the inner radius of x squared dx. And for shells, we're using the circumference formula. So it's going to be the integration from a to b of 2 pi. This is going to be r of x times the radius of rotation, which is going to be x, times dx. I guess I should say it's going to be x minus the axis of rotation, whatever that happens to be. I'm just going to call that r. I ran out of variables. Oh well. You get the idea. There are two different ways to do this. Find the volume of a solid bounded by the given functions or to be about the given line. I'll let you choose either the disk or the shell method. So I have y equals x cubed, y equals 0, x equals to 2 about the x-axis. So let's graph this quickly. I'll pause the video and sketch it. X equals 2 here. I have y equals x cubed there, and I'm rotating about the x-axis. Should I use the disk or the washer method? Well, you could use either one, but I think since this one, the functions are relatively easy to solve for x, I would use the disk method. So in this case, I'm going to set this up but not solve it. What I would want to do is take the integral, and it looks like I'm integrating from 0 to 2 on the x-axis, of pi times the outer radius, the big radius, would just be the height of this function, which would be x cubed, minus the little radius, x cubed squared, minus the little radius squared, which is just 0, because that's the bottom of the rectangle, so that's 0, squared dx. That would be a pretty easy integral to evaluate. Let's use this example here. Here's it done two different ways. I'll let you look at that for a second. So with the disk method, you can see that my rectangles are perpendicular to the y-axis, which I'm trying to rotate around. And I have to separate this out basically into two different functions. For the first, from 0 to 1, it's just going to be pi times 1 squared. That's it. But from here, your distance is going to be 1 minus whatever this function is, which is square root of y minus 1 squared. 1 squared minus that squared. In the shell method, you can see it set up a different way. We're going to complete this exercise in class.